Okay, are we ready? All right, so let us continue with lecture number 4 by Pasha Etingof.
All right. So, last time we discussed the Hitchin integrable system, and we proved the Hitchin's theorem that this system was integrable in the case of GLN or SLN on a curve of genus greater or equal to 2. So today I want to compute some examples. But the problem is that computing for curves of genus greater or equal to 2 is rather difficult because the bun G in that case is pretty complicated, and it is hard to write down coordinates. One can do it. In fact, Turin did it and for GL2, and Krejcir did it, generalized it to GLN. So one can do it, but it's rather difficult. So we will actually consider generalization of Hitchin systems when you have punctures on your curve. And this will allow us to have non-trivial situation when genus is 0 and 1. And those things will be amenable to explicit computation. So, so let me talk first about bundles with parabolic structures. So first, suppose we have H inside G, a subgroup, closed subgroup, and suppose we have E, a G bundle on X. So at this point, this is very general. You can take any variety, any algebraic group. And so we say that so if you have a point X and X, then definition an H structure at X is an H orbit in the fiber EX. Recall that EX is a torsor over G, so it's essentially a copy of G where we forgot the position of the origin, but still we have a simple transitive right action of G on the fiber, and we want to take an H orbit. And so how many possibilities we have? So how many choices do we have? Well, clearly it's parametrized by the quotient G over H. Because it's our essentially H cosets, right? Let's say H cosets on G. And now we're in particular going to be interested in the situation where H is a parabolic subgroup. So let's fix some points, T1 to Tn are points on our curve X, distinct points. And P1 through Pn. By the way, I should say that when we talk about H structures, well, H matters only up to conjugation. Well, in the sense that if we have an H structure, which is an H orbit, and we multiply on the right by some group element G, this will transform an H orbit into GHG inverse orbit. And so suppose these are parabolic subgroups. So parabolic subgroups, so I remind you that G is a connected reductive group, for example, GLN, and parabolic subgroups means they contain Borel subgroup. So these are the subgroups for which the quotient is a projective variety. Connected, there are subgroups for which the quotient is a projective variety. For example, for GLN, if you have a composition n equals to n1 plus n2 plus n r, then a parabolic subgroup corresponding to this composition is the set of all matrices of this kind of form. So this is n1. So this is the corresponding parabolic subgroup. It is the subgroup of matrices with this block structure. In particular, the smallest parabolic subgroup is the Borel subgroup, which is the upper triangular matrices. Okay, so and so now I want to define Ban G of x, T1 up to Tn. So there should be the same. So each choice of parabolic subgroup corresponds to the corresponding point. So P1, Pn. So this is the moduli stack of G bundles on X with Pi structure at the point Ti for I equals 1 through n. So at every, you should think about this picture here. So you have your curve, then you have your points, let's say T1, T2, T3, T4, and then you fix parabolic structures at those points. Parabolic structures are structures corresponding to this group. For example, so the basic example that we are going to consider is, let's say, G equals to, well, GL2 or PGL2, and Pi are the Borel subgroup, which is the subgroup of matrices of this form. And in this case, so how can we think in general about, so I said the choices are the set of choices are G mod H, but it's not canonically G mod H. It's isomorphic to G mod H. So more precisely, what happens in this case? So suppose if G equals to GLN, then what is the fiber of a point of the bundle E at the point X? So we said that in this case, G bundles are the same thing as vector bundles of rank n. And so suppose we have some bundle E, so it's a rank n vector bundle. Well, then what is the, so it has some fibers. So what is the fiber? So the E, let us write a script E to be the corresponding GLN bundle, principal GLN bundles. So we said that they were corresponded to each other, but the fiber of this is a vector space of dimension n, and the fiber of this is the general, a torsor over the general linear group. So what is the fiber of E at a point X? Well, it's actually, it's isomorphic to GLN, but what is it canonically? Well, I claim that canonically it is just a set of all bases in the fiber of the corresponding vector bundle. The set of all bases in a vector space is a classic example of a torsor over the general linear group, because we can make change of bases by a matrix. And so, so that's the fiber. And in particular, if P is a parabolic subgroup, So if P is a parabolic subgroup, then what is a parabolic subgroup? Like I said, it is a subgroup of this form, so it preserves a partial flag. Stabilizer of a partial flag. 0 is contained in V1, contained in V R, which is equal to V, where the quotients have the dimension. I ran out of space. Okay, so let me write here. So the quotients Vi plus 1 over Vi have dimension Ni, corresponding block. And so then the fiber of the corresponding a P structure at a point X is the set of bases compatible with this flag. So this means that there is a subset of the basis which is a basis of each of the spaces Vi. That's just basic linear algebra. And so in particular, in this simple situation, well, fixing, well, with a flag. So a P structure is the same as fixing a partial flag. So that's a convenient way to think about P structures. It's a fixing a flag in the space E sub X. Partial flag with quotients having dimensions Ni. And so in particular, in this case, we have just a two-dimensional space, and we have a complete flag, but fixing a complete flag is just fixing a one-dimensional subspace, a line in Ex. So a parabolic structure, B structure on some vector bundle E, rank 2 vector bundle. So let's talk about vector bundles. It's technically a bit easier. Is just at a point X in X is just a line L inside Ex. So this means that we are fixing a line at every. So we have these fibers Ex, Et1, Et2, Et3, Et4. They are two-dimensional spaces, and in each of them we are fixing a line. And our moduli space or stack is just the set of all such data. So this shows that. Question? Okay. So we have a fibration from bun G of X, T1 through Tn, P1 through Pn, into bun G of X with fiber G, so flag manifolds, partial flag manifolds G over P1 cross G over P2, G over P. Okay, and so So why do we want to consider this? Because the problem, well, first of all, it gives us a more general theory, but specifically, I want to consider it today because that allows us to consider genus 0. Remember that we started last time, we considered genus greater or equal to 2, and there was a good reason for it. That in genus 0 and genus 1, if you don't have marked points on your Riemann surface, you do not have stable bundles. All bundles are going to have non-trivial automorphism groups, even if your group G is adjoint and semi-simple. If your group is a semi-simple and moreover adjoint. And so we weren't able to, and what we need is we want to have generic bundles or stable bundles, which are, roughly speaking, bundles with trivial or finite automorphism group. However, if we put more data, we put these points here and we put these lines, then automorphisms will have to preserve this data. And the automorphism group will become smaller because we're putting more conditions on automorphisms. And in particular, there will be a lot of bundles that will have automorphism group trivial. So in particular, if n is at least 3, then a generic bundle on P1 with parabolic structures has trivial automorphism group. So we have a notion of stable bundle. So there is a notion of a stable bundle with parabolic structures. And there are actually more than one, but it doesn't matter much which one we will use for the purposes that I want to discuss. And let me not discuss this right now. Maybe if we have time, I will explain what this means. But basically, you can take just the trivial bundle. So let E be the trivial bundle. And in this case, the automorphism group of E. So let's talk about PGL2 bundles. So which means these are vector bundles of rank 2 modulo tensoring with line bundles. So the automorphisms is just the group PGL2. Because we just have the trivial bundle. All the fibers are canonically the same. And that's because a holomorphic function on a compact Riemann surface has to be a constant. So, but then, but we have parabolic structure L1 through Ln, where Li, all of these Li lie in the projectivization of the fiber of E at the point Ti, but all these fibers are the same. They're just C2. So this is just P1. This is standard P1. Yes. So there is a notion. So we have a notion of a principal vector bundle. Automorphism of a vector bundle is this means there are many ways to think about it. So one think of it is it's a section of E tensor E dual, which is non-degenerate at every point. Another way to think about it is on every open set where the bundle trivializes, it is just a regular map from this open set to GLN, such that these maps agree on the intersections through the clutching maps, and so on. So there's automorphism. Any kind of structure we define, there is a notion of automorphism. So in particular, for trivial bundle, automorphism is a holomorphic function on the entire X with values in GLN, which is a matrix-valued function. with a determinant non-vanishing. But of course, such a function has to be a constant because our Riemann surfaces compare. And so we just get a matrix. Right, exactly. So actually there is a whole point on this Hitchin story, which comes from differential geometry rather than algebraic geometry, where you actually define Hitchin moduli space not as a cotangent bundle to bund G, but as a space of solutions of certain PDEs, which are called Hitchin equations, and which are the Young-Mills equations for the two-dimensional gauge theory. But we are not going to discuss this point of view. Questions? Okay. So we get an action. So PGL2. So the set bon G of X T1 Tn P1 so let's say when I have Borel subgroup, I'm not going to write my P's. And so the set, let me write triv, parabolic bundles with parabolic structure, which are trivial as just vector bundles. So this set is just, it's an open subset in the whole stack because generic bundle is trivial. Well, it is just P1 to the power n quotient by PGL2. So this is a much more explicit space on which we can do computation. Note that this is still a stack because there are some points here. So this is just collections of n points, but there is still stabilizers. For example, if all points coincide, there is a stabilizer of a point on P1, which is the group B of upper triangular matrices. Yeah. So, but inside this contains an even smaller open set. Of tuples of points y1, yn. So here there is some vector of points y1, yn, where let's say y1, y2, y3 are distinct. And it is well known that PGL2 acts simply transitively on triples of points on P1, which are all distinct. So in particular, this subset is just so we can, there is a well-known theorem that if you have 3 points on P1 which are all distinct, there is a unique element of PGL2 that maps it to 0, 1, and infinity. And then, so we will get that this open subset is just P1 to the power n minus 3, because they will still have the other points. But we no longer have any stabilizer. We no longer have any group acting, because we killed all the symmetries by making the first point 0, the second point 1, and the third point infinity. And this is already a variety. Okay. So, but this, so we are going to live basically on this stack. I mean, it is slightly stacky, but you know, it's much simpler than the general thing. And we will be able to do calculations using these coordinates. So these yi are going to be in P1, which is C union with infinity, Riemann sphere. Okay. So in general, Bon G with trivial as an abstract bundle of X T1, Tn, P1, Pn is just the following space. It's the product over I of the flag manifolds G over Pi and quotient by the diagonal action of G. So this is still a stack, but it's much simpler than the general stack of all bundles. So now I want to so we can still talk about the Hitchin system. So the next thing is Hitchin system with parabolic structure. And it generalizes rather straightforwardly because, so remember that Hitchin system was constructed by realizing the bond G as a double quotient and descending a certain collection of Hamiltonians upstairs on the cotangent bundle of the loop group down to the double quotient. Well, we can still represent it as a double quotient here. So double quotient representation of bond G T1 Tn P1 Pn. Well, it's actually quite easy to do. So recall that bond G of x is just double quotient G of so let me realize it. So I explained that there is a realization when we take out these points T1 through Tn. So let Zi, Z1, Zn are local coordinates near. Well, maybe I don't need even to introduce coordinates. Let me just work canonically. So so this is a product over I of G of the punctured disks around the points Ti over the product over I of G of the ordinary disks non-punctured, and on this side G of x minus T1 Tn. So that's the usual bond G. But now, if we want to fix parabolic structures, then of course, this is the data at the points Ti. And so this group of all functions on the disk Ti around Ti. So we have this picture here. Again, we have points T1, T2, T3, and T4. And then we have these infinitesimal disks around them, DT1 and so on. And we're using two charts. One chart is the union of those disks. The other chart is the complement of these points. And so the parabolic structures are local structures at the points Ti. So this means that we have to change something on this side. And in fact, it is clear what we should do. So we have a homomorphism from G of D to G, which is the evaluation map, evaluates it at the center. So evaluation of G of Z is just G of 0. Evaluates a function on the disk at the center. And then we can define the groups Pi tilde, which is pre-image under this map of the parabolic group Pi. So in other words, it is all Taylor series where values in G, such that the constant term lies in Pi. And then we just see that bond G of x, T1, Tn, P1, Pn is simply the same thing, but with these groups replaced by the Pi tildes. So it is the product over I, G of dx, dti times over the product over I, Pi tilde. And on this side, G of x minus T1 Tn. This is clearly fibers. So this statement here, that we have this fibration over there, is clear from this presentation because we just replaced the product of G over dTi by product of pi tildes. So the error we make is the discrepancy will be the product of quotients of these groups by those, which is the same as G mod pi, because the only difference is in the constant term. Okay, so we've got that. And so now we can take the same Hamiltonians pi of phi on cotangent bundle of this loop group. So we did it for one puncture, but the same thing works for any number of punctures. And so cotangent bundle of G of dt1, cotangent bundle G of dtn, and do reduction, Hamiltonian reduction with respect to G of x minus Ti times the product of pi tilde. And then we obtain an integrable system on bond G of T1 Tn, P1 Pn. So one can show that Hitchin's theorem extends to the setting. On T star, yes. So as before, so we have infinitely many. So these are actually infinitely many. So this is Hin, which is a residue of this multiplied by Zi to the n. And so there are infinitely many Hamiltonians here. They descend to here. They become linearly dependent. But still, the remaining ones, which are independent, come in the right number and form an integrable system. So I'm not going to prove it, but we will compute what happens in the example of GL2. So what will we get then? So what is this thing here? Well, this is a set of pairs, E phi, where E, we know what it is. E is a parabolic bundle, which is a bundle equipped with parabolic structures. But what is phi? So phi is a Higgs field. But, of course, now we have a bigger space of E's that is bigger by the product of the flag manifolds. So it has bigger dimension. So we should also have similarly bigger space of Higgs fields because it has the dimension has to increase by the same amount. So this means that it's not just enough to take Higgs fields for the bundle E. So we actually should allow singularities. So that previously Higgs fields were just holomorphic. But now we should allow singularities at the punctures. And so you can check that the correct condition is the following. So with singularities. And the condition is the following, that phi has at most first order poles. So remember, phi is one form with values in the endomorphisms of E. One form on X with values in adjoint bundle of E, but it is now can be singular at the points Ti. And so it has at most first order pole at the points Ti, and the residue strictly preserves the flag Fi at the point Ti. So remember, specifying a parabolic structure means that we specify a flag at the point Ti. So Fi is a flag in the fiber, but strictly preserved means it's a Lie algebra element. That's right. Yes. So this means it lies in the unipotent radical of the stabilizer. Lies in unipotent radical of the stabilizer of Fi. So in particular for usual flags or partial flags for GLN, this means flag is a filtration on our space, and strictly preserved means that it maps I space of the filtration into I minus 1 space. So it acts by 0 in the associated graded. Which group? Yeah, it acts freely on some open set. So like I said, that there will be lots of generic bundles with trivial group photomorphism. So the stabilizer, so if you represent something as a double quotient, this means that this product of these groups acts on this group. And the stabilizer is the basically intersection of this with the conjugation of this. And this will be exactly the automorphism group of the bundle. So in this case, with parabolic structure. So for generic bundles, it will be trivial if we put enough points, even in genus 0. Other questions? Okay. So now, so this is an exercise to check that this is the right condition, because of course we discussed that cotangent bundle of bond G is a H1, a certain H1 group of X with coefficients in the adjoint bundle. So here this will have to be amended somewhat by considering singularities. So maybe I should call this as an exercise. But this is the correct condition. So in particular, for PGL2, so phi has simple poles at the points Ti, and phi and residue of phi at the point Ti is nilpotent and acts by 0 on the line Li inside the fiber of E at Ti. So, by the way, when I talk about residues, you might object and say that, well, we can only talk about residues of differential forms. Well, in our case, it's a differential form with values in some bundle. But of course, when we take residue, we obtain just a section. We just obtain an element of endomorphisms, and so this makes sense. And in fact, it doesn't even matter, because when we for this condition, it matters only up to scaling. So it really doesn't really matter. Okay, but so that's the condition. And so let's compute now. So now let us compute the Hitchin system for PGL2 in genus 0. And so for this purpose, we will assume that the points T1 through Tn actually belong to A1 inside of P1. So they're just complex numbers, just for the convenience of computation. And parabolic structures at Ti is going to be Yi. Well, again, it's in P1, but I'm going to assume that it's in just in A1. So this means that I take Yi corresponds to vector Yi1 in C2. And the line Li is spanned by this vector. Okay, so now, so what is a Higgs field now? So Higgs field is a one form with simple poles at Ti valued in SL2. So this means that phi is going to be the sum of over I from 1 to n of AI divided by z minus Ti times dz. But it should be regular at infinity because we don't have, and so these AI are in SL2. And then it should be regular at infinity because at infinity we don't have a puncture. So a form like this is regular at infinity if the coefficient of dz has a second order decay because the form dz over z, for example, is singular. dz over z squared, dz over z cubed are already regular because dz over z squared is differential of 1 over z up to sine. And so this means to have a condition that the sum over I of AI equals to 0. Huh? Yeah. I'm not done yet, of course. All right, and then so also we want these residues, AI, they should be nilpotent, and they should kill the vectors yi1. So let's compute what that means. So suppose you have A nilpotent and kills the vector y1. So A is equal to A, B, C, D. And so we've got A, B, C, D times y1 is 0. So we've got AY plus B is 0, and CY plus D is 0. Okay, so we can compute everything in terms of C. So first of all, D is minus A, because we need trace 0 for nilpotent matrix. B equals to minus AY, and D equals to minus, so D equals to minus CY. So this means that A equals to CY, and D equals to minus CY. So we've got that A is CY minus CY, and then B is minus AY, but A is minus A is CY. So we've got this is minus cy squared. And finally, this is just c. And so this means that for each I, I'm going to have ai is equal to, well, let me call, in this case, c by pi, because it turns out that these, so yi are coordinates on our space, and pi are momentum variables. It turns out that they are canonical coordinates. So the symplectic form will be sum of yi dpi. And then ai is going to be pi. So there is an overall factor pi. And here is going to be yi minus yi squared minus yi and 1. Okay? So we see now we still have an PGL2 symmetry. I did not kill it. So this means that we will write some system in terms of these y's, and then we should take reduction with respect to PGL2. So it will be invariant. This system that we will get is projectively invariant. I could kill it, but then the computations would become more ugly. So it is better to keep it in the game. And so this way we have n phase space of dimension 2n. We have n y's and n p's. When we do complete reduction, we will get, as I said, n minus 3 dimensional space of y's and n minus 3 dimensional space of p's, but the formulas will get ugly. All right, so let's compute our Hitchin Hamiltonians. So in this case, we only have quadratic ones, right? Because we have PGL2. So we have H N2, which is, let me write 1/2 of the trace of phi squared. Well, we can calculate what this is. This is 1/2 of trace of the sum of ai over z minus ti, aj over z minus tj for I and j. But now I equals j drops out because ai is nilpotent, so ai squared is 0. And of course, the terms with ij and ji are the same. So we're going to get the sum over I less than j of trace of ai aj divided by z minus ti times z minus tj. And so, well, of course, everybody knows that we have this identity 1 over z minus a, 1 over z minus b equals to 1 over a minus b, 1 over z minus a minus 1 over z minus b. And so this can be written, therefore, as the sum over I different from j, trace of ai aj, or ti minus tj, times z minus ti. Okay, so now it remains to calculate this trace of aiaj. So the trace of aiaj is pi pj times the trace of what? Yi minus yi squared, 1 minus yi, times yj minus yj squared, 1 minus yj. And we only need to compute the diagonal elements. So we've got pi pj, and then what? Well, we've got yi yj minus yi squared plus yi yj minus yj squared. So this is equal to pi pj with a minus sign times yi minus yj squared. And so, so now we, well, remember this is a function of z, so there are infinitely many integrals. But we can extract integrals by taking coefficients of that with respect to z. In particular, here we can take residues. By the way, this is, I should write here the dz squared, which I have skipped because it's a quadratic differential. And in particular, we can take residues at the points ti. So, so let's take gi to be a residue of h n2 at the point ti. So at this point, we have trivialized everything. So we can take residues of quadratic differential functions or anything we want. So this is equal to what? Well, this is just a value, just the numerator here, which would be I is fixed. And so this is going to be the sum over j different from I, pi pj yi minus yj squared divided by tj minus ti. And so we obtain an integrable system with integrals like that. And this is the so-called Garnier system. Okay, any questions about this? Can you speak up, please? How to take residue? It doesn't matter. At this point, I trivialized my coordinates. It doesn't matter. I mean, okay, if I change coordinates, it will multiply by a scalar, but it will still be an integral of this flow. I'm just writing down some. So this thing is basically a generating function for integrals of my flow. And so, so there are n integrals here on a phi space of dimension 2n. The sum of these gi's will be 0, but when after reduction, this will become an integrable system. Because it has symmetries, so after reduction, we'll have integrable system. Yeah, for the trivial bundle, we took the chart where the bundle is trivial because generic bundle is trivial. So then the question is what happens, for example, when we come to certain singular points, so this flow extends to a bigger space. And that's an interesting question. This is an example of when integrable systems initially defined on some simple space extend to a bigger space. But I'm not going to discuss this. Yes? Well, there will be additional coordinates corresponding to moduli of the bundle E. So here we use the fact the generic bundle on P1 is trivial. That's no longer the case even for elliptic curve and also for higher genus. So there will be parameters of G bundles. And so we will still have to have coordinates corresponding to variation of G bundles. And the story will become much more complicated. You can still write things in Turing coordinates, for example, but it's going to be much more complicated. Yes? No, this is just in this case, it is a sum of simple fractions. It is sum of something independent of z divided by z minus ti. So I just take the residues of this thing. It's already expanded in partial fractions. Yes? Yeah, you can compute what happens. So parabolic points can collide. And then what you normally get, well, if you want to get some interesting answer, You should also do twisting, which is what I will explain in a second. But in that case, you will obtain some confluent versions of this system. Yeah. There will be some integrable systems which are obtained by limit of this. We should consider Garnier system with parameters, which I will do in a second. And then if you collide points and simultaneously send corresponding parameters to infinity, you will get interesting limits. Yes. Oh, well, some open set there is p1 to the power n minus 3. Well, here we're working on p1 to the n, or rather a1 to the n. So our space that we're working on is really T star of Cn, because we didn't kill the SL2 symmetry. So we only took reduction with respect to, let's say here, with respect to the group. So we took here functions which vanish, which are equal to 1 at infinity, so smaller group. And then to get the full picture, to get down to the actual Hitchin system, we have to do another step of Hamiltonian reduction by PGL2, by G. And we did that in order to make formulas nicer. So now you can compute. So there is this integrable system. So on this thing acts the group PGL2. And you can take a reduction with respect to that group of this integrable system, and you will obtain an integrable system on n-3 dimensional space. And you can compute the Hamiltonians, but the formulas will be less nice. No, not well. Well, you see, it's this. So actually, here we also, I lied when I said that we have an integrable system here, because the sum of these gi is actually 0. The sum of ti times gi is also something fixed. The sum of ti squared times gi is also something fixed. So this means that we have 3 integrals fewer than we want. But instead we have a SL2 symmetry. And so, so we can kill it, and then we will get a true integrable system. So that's a more honest way of explaining it. Again, this is something that is easier maybe to say if we consider some deformation, which I am going to explain. Yes. Do we have the same? Yeah. That's what I'm going to explain. There is a twisted version where we don't require them to be nilpotent, but rather they have a certain particular eigenvalue. Yeah, I'll explain. That's what I was going to explain. Other questions? Yes. Very loudly, please. Yes. I'm sorry, I didn't. Well, they are tangent, they are basically cotangent bundles. So we have these flag varieties here, and these correspond to elements in the cotangent space to the flag variety. In this case, we do not have moduli of bundles themselves. We are considering trivial bundle, and everything comes from these flag varieties. Okay, other questions? All right, so I will now explain a twisted version. Actually, I don't want to erase this, so let me just erase this here. So the twisted Hitchin system. And for this purpose, I first have to explain Hamiltonian reduction along orbit. So suppose, so I explained that if you have, let's say, M, a symplectic manifold, we talked about cotangent bundle, but more generally, just any symplectic manifold, and you have a group H acting on this M, then we have suppose we have a moment map from M to H dual, and this is in general, it's just a piece of data. It doesn't always exist. Well, then we can define this reduction, mu inverse of 0, modulo H. This is the Hamiltonian reduction, which we discussed. And if the action is nice, if H acts freely, in nice cases, this is a symplectic manifold. Well, this has a generalization. We actually can take pre-image not of 0, but of any invariant, or for any coadjoint orbit of H star. More generally, can consider mu inverse of O over H, where O in H star is an H orbit. So any coadjoint orbit has a canonical symplectic structure, which is a so-called Kirillov-Kostin structure. So using this, you can check that this will also have a canonical symplectic structure. And so, in particular, and then you can do so we can run the same story. So we can run the same construction with integrable systems. So if you have some functions fi in involution on M, and fi are H invariant, then they descend to functions fi bar on this reduction, mu inverse of O over H, which are also in involution. And the proof is the same, actually. So, and sometimes you have, too few functions upstairs, but when we go downstairs, you have just the right number. And we can apply this procedure to, so this gives us a more general class of integrable systems, and in particular, we can apply it in the setting of Hitchin systems. So we can do reduction along orbit. So for example, in this situation, we have product of G of disks dti punctured, and inside here we have g of x minus t1 tn times product of g of dti. So we can take we can do reduction. So reduce first by so this maps to the g to the power n by evaluation at t1 through tn. And this there is some kernel k of this evaluation. Let me call it ker. So we can first reduce by ker, and then get a residual action of the quotient group, which is this. And then we can take some orbit O inside G star to the n, and then we take mu inverse of O over G to the n, and descend Hitchin Hamiltonians to this quotient. And so this procedure means, so let's see what this procedure does in the case of PGL2, which we have played with today. No, at the moment there aren't. We will see how this is related. So parabolic structures will be related to the case when we take this to be the biggest nilpotent orbit. Huh? No, just any, well, I mean, you need some sort of freeness of the action. But as long as it is free, then this will work. Okay, so let's see what the condition will be. So this should create some condition. So this mu inverse of O modulo G to the n will be the set of pairs E phi. But the condition on phi, so this will be some sort of twisted cotangent bundle of parabolic bundles. But so let me just explain what the condition on phi will be. So the condition on phi will be that it's going to be so I'm going to so we still have so let's take G equal to PGL2, and then orbits. So we have to fix orbits, coadjoint orbits for G dual for all points. So so orbits in SL2 dual, which is SL2, will be at the points Ti. We will fix the orbit lambda I 0 0 minus lambda I. So let's say we have this orbit for generic number lambda I, which is not 0, let's say. So then the condition on phi will change. So the previous case also corresponds. So you can check that the previous case with parabolic structures, ordinary Hitchin. It corresponds to fixing the orbit of nilpotent element, which is a limit of such things. If you put 1 here, it's the same conjugacy class, and then it goes to 1 to this when lambda goes to 0. So the condition on phi will now be phi has simple poles at Ti, and the residue at Ti of phi doesn't kill Li, but on Li it acts by eigenvalue lambda I. This is surjective. What? Yeah, but that's here I'm saying something different. So there is this big group, and it projects surjectively into this. And then I have some kernel. So I can reduce first by the kernel in the usual way, and then I can reduce by this residual group G to the n using an orbit in the coadjoint representation of this group, which is this. This? I evaluate, well, it's this maps to 1. I mean, this ignores this factor. And then for these factors, it just evaluates these at the centers of these disks. Okay, so we've got this condition. So again, phi is going to be the sum of AI over z minus ti dz. But now the equations will change. So instead of the equations over there, we're going to get that AI times yi1 is not 0, but it's lambda I times yi1. So let's compute what happens in that case. Okay, so we do this calculation again. So A times y1 equals to lambda times y1. And this is A, B, C, D. So we've got A, y plus B equals to lambda y. And cy plus d equals to lambda. So, so we've got the d is equal to lambda minus cy. And this means that A equals to minus lambda plus cy because the trace must be 0. And then B is equal to lambda y minus ay, so lambda minus a y. And lambda is this, so this is equal to 2 lambda y minus cy squared. So we've got the following matrix. Minus lambda plus cy, lambda minus cy, 2 lambda y minus cy squared, and then this c. And so this means that the matrices AI are going to be as before, but with this lambdas. So minus lambda I plus pi yi, 2 lambda I yi minus pi yi squared, pi, and lambda I minus c minus pi times yi. And so then you can compute the trace of AI, aj. So that's the only thing that will change, the formula for this trace. So we're going to get some additional terms. So we will get some additional terms. So the usual thing, minus yi minus yj squared pi pj. This is without the lambdas. Then there is a quadratic part, and this is going to be twice lambda I lambda j, which is just a constant, so it doesn't really matter. And then there will be the interesting term, which will be 2 lambda I pj minus lambda j pi times yi minus yj. So that would be the correction that we get from the lambdas. And so therefore, what we will get is, okay, so we will get the deformation. So we get the deformations, gi of lambda 1, lambda n is going to be the sum over j different from I. So here is going to be ti minus tj, maybe tj minus ti. And here is going to be minus y1 minus y2. Yi minus yj squared pi pj plus twice lambda I pj minus lambda j pi times yi minus yj plus twice lambda I lambda j, like this. And so that's a deformed or twisted Garnier system. But the problem is, so okay, so when you take the trace, okay, so I used before that ai square is 0. Now I square is not 0. Now a square is a scalar matrix. Yeah. But that term will only contribute constants, so I threw it away. No. So let's go back. So we have the following function. So there's going to be the sum. So trace of phi, 1/2 of trace of phi squared is the sum over I and j of trace of ai aj 1/2 over z minus ti, z minus tj. I am going to drop dz squared. And so in particular, this equals to 1/2 times the sum of trace of ai squared, which is really 2 lambda I squared, because this is a function that has eigenvalues lambda I and minus lambda I, divided by z minus ti squared. So in this case, we do have a term which vanishes, which has a second order pole at ti. But if we only take the coefficient at ti at minus 2 second power of the coordinate, we will just get lambda, which is a constant. No, they are not interesting because they are not, okay. And for integrable systems, they are not interesting because we're trying to construct some Hamiltonians. Constant is not a very interesting Hamiltonian. Yeah, and in fact, this term is also not very interesting. We can drop it out. So the interesting part is everything else. Okay. So now, so this is the deformed Garnier system. And finally, I want to explain how elliptic Calogero-Moser system can be, and its Lux matrix discovered by Krichever can be seen as a special case of the Hitchin system. And the previous was what? Yes, exactly. Yeah, so that's a limiting case, which is resonant, which is where this matrix is not semi-simple. And that corresponds to parabolic structure. So then the lambdas are going to drop out. And so that's why that corresponds to what I said before, that ordinary story with parabolic structure corresponds to taking nilpotent orbit, as opposed to a semi-simple orbit. So when we do reduction with respect to a semi-simple orbit, what we will obtain is not the usual cotangent bundle of our space bond, but actually something that's called twisted cotangent bundle. But it doesn't matter at the moment. So let's talk now about genus 1. So X is an elliptic curve. And so what do generic bundles on elliptic curve look like? So let's consider generic bundles, let's say of degree 0, of rank n. Well, they are direct sums of line bundles, but in this case, line bundles have parameters. So, so let's say L, so there is a 0. And there is an L sub A, where A is an X. So line bundles of degree 0 are elements of the Jacobian. Jacobian of elliptic curve is the curve itself. So we have bundles LA, A in X, which is really O of A times O of 0 to the minus 1. And the section of this LA is this function that appeared already many times, theta function of Z minus A divided by theta of Z. So this section is meromorphic. It has a pole of first order at 0. This, for A different from 0, this does not have holomorphic section, but it has a meromorphic section, which is this thing. And this section really defines this bundle. And so generic bundles, and so these generic bundles are of the form E is equal, so Atiyah showed that they have the form, and it's not difficult. They have the form LA1 plus so on plus LAN. And let's say AI are distinct. Okay? So now, so suppose we put a parabolic structure. So let's consider the case of G equals to, let's say, PGLN. And then we put one puncture at 0. And put the, and do the twisted reduction there. For the orbit O inside the Lie algebra. So O is generated by the matrix. So let's put matrix 1, 1, 1, and minus n plus 1. So it's a kind of simplest semi-simple orbit. It is the smallest semi-simple orbit. It consists of matrices which have eigenvalues n minus 1 eigenvalue 1, and 1 eigenvalue minus n plus 1 to balance out the trace to be 0. Okay? So we do reduction with respect to this. No, they're semi-stable. These bundles are semi-stable. There is no stable bundle. A tier has stable bundles of degree 1. For degree 1, there are stable bundles, but there is only one stable bundle. So, if you just consider stable bundles, you will get the differential equation on one point. It's not very interesting. It's invariant under shift. No, you cannot get anything interesting if you don't introduce this orbit. Okay, so and so this orbit corresponds to really taking maximal parabola. So if you degenerate this orbit, well, I mean, you can put C here. So let's put C, 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 and then minus n plus 1 C. So when C goes to 0, this orbit degenerates to this one. So it's nilpotent matrices of rank 1. And this corresponds to the maximal parabolic subgroup, which has n minus 1 times n minus 1. Here is 1 by 1. So that's P. So this means flag variety for this case is just projective space, P n minus 1. Because the flag is just a line, fixing a line inside, or if you like, a hyperplane. So it's a projective space. So let's think about it as a set of lines. And okay, so what is the automorphism group of this bundle? So automorphism group of E is the torus, right? Because there is no maps from LA1 to LA2, for example, because AI are different. But there are endomorphisms of LA, which are numbers. And so automorphism of this is C star to the power n. And so this acts on this projective space. And we need to look at free orbits. So free orbit is unique. Well, no, well, it's a PGL. So I have a PGLN. So that means it's that. Well, okay, so there is a free orbit of the vector where all entries are non-zero, and then I can make all of them 1. So that's a parabolic structure I should use. And then my moduli space is going to, the coordinates on my space are going to be these A's. I don't get any coordinates from the parabolic structure because we haven't, everything is equivalent. All vectors are equivalent. But I do get these variables now. So these are going to be my position variables. Okay, so now let me actually call them Q so that this is reminiscent of classical mechanics. Okay, and so now what is my Higgs field going to look like? Well, it should have pole. So first of all, so phi is my Higgs field. And it's going to be, if I realize these bundles as trivial bundles outside of the origin by using these functions, I can think of it as, anyway, I can think of phi as a matrix phi ij, where phi ij is a section of LQI tensored with LQJ inverse. So this means, and I want a first order pole at z equals 0 and residue preserving. So this is L of Qi minus Qj, and residue preserving my vector 1, 1, 1, 1, and acting with eigenvalue c. This c is going to be immaterial. We can rescale it at the end, but I still want to keep it around. All right, so this means what? This means that phi ij, this bundle has only one section up to scaling, which is with first order pole at 0. And so this is just theta of z minus qi plus qj divided by theta of z. So here we should put some aij. And of course, this is when I is different from j. And then phi ii is a section of the trivial bundle. So this is actually just some pi, which is going to be momentum variables. Now, what can we say about this matrix? So in this case, we cannot have a pole. So what is the condition for the matrix A? So this matrix A should satisfy the condition that A111 equals to C times 1, 1, 1, 1, right? But then, well, what is this? So this means that so the matrix A has zeros on the diagonal, and it should have rank 1 up to adding a scalar. So this means that all the entries of this matrix which are off diagonal should be the same. So A, I are 0, and A has only 2 eigenvalues. So actually, eigenvalue probably n minus n plus 1 times c, whatever. Anyway, so this has only 2 eigenvalues. So this means that all aij are the same. And A, if it preserves this line, then this means all eigenvalues, all elements are the same. So that's easy to check. And so what you get is that phi ij equals to some constant, well, let me call it c, times theta of z minus qi plus qj over theta of z. And so, so here is our matrix P, and this is Krichever's-Lax matrix for. Oh yeah. I'm sorry. Of course. Because I want a residue, right? And residue at 0 of this thing is going to be okay. You have to. This has derivative 1, and so I have to evaluate z, and so j minus q. Yeah, I don't normalize theta this way. Okay, so so I've got my matrix A, which is going to be well, my Higgs field phi is going to be well, P1, Pn. And here there is going to be this thing, constant, times theta of z minus qi plus qj over theta of z, theta of qj minus qi. And then you can compute the trace of phi squared. And this is going to be the sum of pi squared plus the sum over j different from I, so c squared times theta of z minus qi plus qj, theta of z minus qj plus qi, divided by theta of qi. This is an odd function, so this is just square. And so here maybe it is a minus, I don't remember. But in any case, what this is, again, everything now depends on this z. So as before, this is a generating function. And then there is a theta of z squared. So if you take, so you need to take some coefficient. So if you take a z inverse z to the minus 2 coefficient, you will get, well, this will evaluate to 0, this will evaluate to 0, you'll just get a constant. So it's not interesting. So the interesting thing you will get if you take the constant term of this Laurent series in Z. So the constant term is going to be the sum of pi squared plus c squared. And then the constant term is going, so this thing, actually, you can check. This is just the Weierstrass p function minus the Weierstrass function of qi minus qj. That's easy to check because this vanishes in the right places and has the correct poles. And so what you will get is that this is the sum. So the p function has trivial coefficient for z to the zeros. And so you will get minus c squared times the sum I different from j, p function of qi minus qj. And this is the elliptic Calogero-Moser system. So this is the quadratic Hamiltonian, which is elliptic Calogero-Moser system. And this gives us integration of this system because now we can consider traces of exterior powers of phi. And these are going to give us higher Calogero-Moser Hamiltonian. So this phi is it's Krichyver's lax matrix for elliptic Calogero-Moser. Huh? Or traces, well, phi is an operator, right? It's a matrix, so we can take traces with exterior powers. Or we can take traces of powers also, but that's less nice. Okay, any questions? That's it for today. And so on Friday, I'm going to explain quantum story.
Okay. Questions can be asked again at the discussion session. Lunch.